Okay, as promised, here's the video for the second part of the notes. You'll find these in yesterday's post, although I could also update it and post it for today. So now we have another strategy for how to find a series for a function that we're given. And it's kind of crazy, but also really cool. So the fourth strategy, if I were on the first page, I would have put it as the fourth one, is I can take the integral or derivative of a series I already know to get the one I'm looking for. So it's crazy, but also cool. So the idea is this. Let's say I'm supposed to find a series for the natural log of 1 plus x. Clearly, this is not geometric. It doesn't look geometric. There's nothing I can do to figure out what the first term is and the multiplier is. So I can't use that strategy at all. I also can't use substitution because I have nothing to substitute this into because I don't have any series that look like this. But what I do know is I know the series for 1 over 1 plus x. This is geometric, and I can easily figure it out. A is 1, r is negative x. I also know that, I'm going to erase this in a second, but I'm going to write it down here. I also know that the integral of 1 over 1 plus x equals the natural log of 1 plus x. You may not remember that you know that, but you do know it. Let me just give you a little background. Remember, the integral of 1 over x dx, that's the natural log of x. So if I don't multiply x by anything, I don't have a coefficient here. The integral of 1 over 1 plus x would also just be the natural log of that denominator. So this is something I know. I know that the integral of 1 over 1 plus x is the natural log of x. Well, that means if I find the series for 1 over 1 plus x, I can integrate both sides of this equation and end up with the series for the natural log of 1 plus x. Yeah, it's crazy. So let me kind of explain more. So let's start by saying, okay, we know that 1 over 1 plus x is this series, 1, and then we have minus x, and then we have plus x squared, minus x to the third, plus x to the fourth, and so on. So if I want to find this series that I'm given, I'm going to literally integrate both sides. Totally legal mathematical move. The integral of 1 over 1 plus x is the natural log of 1 plus x. So from this side, I get this, which is the function that I'm looking for. And on this side, I have to integrate each term. Yesterday, when I added 1 to a series, I was just adding like terms. I wasn't worrying about adding 1 to every term. That would be actually adding infinity. I was just adding 1. But here, I'm integrating the entire side. So I'm taking the integral of the entire side, which would mean taking the integral of each term. So I need to go term by term here and integrate this right-hand side. So what's the integral of 1? The integral of 1 is x. Pardon me. The integral of x is x squared over 2. The integral of x squared is x to the third over 3. Integral of x to the third is x to the fourth over 4, and so on. And there we go. That is my series for the natural log of 1 plus x. Crazy! Crazy, right? So my answer to what is the series for natural log of 1 plus x? It's this. And then what's the general term? Well, this is the same as, oops. Let me actually just write it over here. This is the same as, so I have an alternator because my signs change from positive to negative. I'll fix this n in a second. And then I have x to the n over the same number, right? My power and denominator are the same. So that would look like x to the n over n. I'm going to start at n equals 1 because that will give me the first term that I need. The only problem is the alternator. My first term should be positive. Oh, sorry, I had to double check that for a second. Yeah, my first term should be positive, so I'm going to have this be n plus 1 or n minus 1. But that's it. So now I just wrote a series for something I never could have written a series for before. So I just took, get out of there. Sorry. I just took the natural log of 1 plus x. By finding a series that I already knew and integrating it, I found a series for natural log of 1 plus x, and I wrote its general term. Crazy. So this is another one that you're going to have written down somewhere, and I'll give you a list of the ones that you should kind of have, that you should know off the top of your head. Okay, so let's look at inverse tan. The reason why we look at these two are because they are ones that I know the derivative or the integral of. I can take the derivative or integral of something I know and get to tangent of x, or inverse tan of x. So think about inverse tan. I do not know the series for that, but I do know that the integral of 1 over 1 plus x squared is arctan. Do you remember that? So what's the derivative of arctan? The derivative of arctan is 1 over 1 plus x squared. So the integral of 1 over 1 plus x squared is arctan. So I have a starting spot. I have a place, because I know what the series is for 1 over 1 plus x squared. So I can say, well, I don't know what this is yet, but I do know the series for 1 over 1 plus x squared. I know that series starts with a is 1, r is going to be negative x squared, so I'm going to have a minus x squared, plus x to the 4th, minus x to the 6th, and so on. So I know my series for that. And now, if I integrate both sides, I'm going to get the integral of 1 over 1 plus x squared is arctan. And I can take the integral of each term here. So I'm going to have x minus x to the 3rd over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on. And that gives me, here's arctan, here's the series for arctan. Now, how about that general term? General term's a little weird here because for the first time, oops, what are you doing? Sorry. For the first time, I have odd-powered terms. Everything else I've done so far has had consecutive powers, really. X to the 1st, 2nd, 3rd, 4th, and 5th, and so on. This does not. So how am I going to write this general term? Well, first of all, I do have an alternator. My signs are going to change every other. And then how do I indicate? I can't just do x to the n over n, because that would mean I would have x to the 1st and then 2nd and then 3rd, but that doesn't happen. So instead, what am I going to make those powers? Well, in general, whenever I want to represent an odd number, I'm going to use 2n plus 1. And whenever I want to represent an even number, I'm going to use 2n. If you think about that, when I plug in numbers for n, like if I look at evens first, if I plug in 1, I would get 2. If I plug in 2, I get 4. Plug in 3, I get 6. But so this expression would give me all the even numbers in a row. And this expression, if I plug in n is 1, or actually if I start with 0, I would get 1. Plug in 1, I get 3. Plug in 2, I get 5. Plug in 3, I get 7. So I get all the odd numbers using this expression. So my power of x is going to be 2n plus 1. And the denominator is going to match the power of x. I'm going to start with n being 0. Because n being 0 will make this be x to the 1st over 1, which is what my first term is. And then my power of the alternator can just be n, because I want the first term to be positive, which it will be if I start at 0, and the next term to be negative, which it will be because my next term will be n equals 1. So now this is the general term. If you understood everything I just said, that's great. You're in a great spot. Okay, let's look at one more. So now I'm given this. I don't know an integral. I don't know what would really come before it. I mean, I guess I could figure it out. It's just a little bit trickier. So I'm going to do this as a derivative. Oh, I'm really sorry to yawn. So for this one, let me write it out here. We know that if I have a function of 1 over 1 minus x, the derivative of that, so the derivative of 1 over 1 minus x, let's think about what that is for a second. So 1 over 1 minus x is the same thing as 1 minus x to the negative first. The derivative would be negative 1 times 1 minus x to the negative second. Chain on the derivative of the inside, so times negative 1. So the derivative would actually be positive 1 over 1 minus x. Oops. Squared, which is what I'm looking at over here. So all of this work just showed me that, hey, if I start with 1 over 1 minus x, since I know the series for that, the derivative of that series is the one I'm going to be looking for. Crazy, but true. Now, before I even start, I want to answer the question, are you going to have to pull this stuff out of your butt yourself? No. I'm showing you how to find some series by using series that we already know and taking derivatives or integrals. You're not going to have to come up with them yourself. What you will have to do is you might be given a series and asked to find the derivative of it, and you're going to do that. You'll see how it goes. It's going to be okay. But I know this work of me being like, oh, hey, look, magically, I know that this series, if I take the derivative of it, gives me what I'm looking for. All of that magical stuff that I'm doing down here, that all this figuring out, is something that I know because I've studied it and looked it up. It's not something that you have to be able to always pull out yourself. So let's do the problem. I'm going to do this in red. It shows up better. So let's start with, we know the series for 1 over 1 minus x. This is our most basic geometric series. Starts with 1. We don't even have an alternator for this because our r is positive, and so on. Well, we also know that if I take the derivative of this and the derivative of this, I'm going to get to the function that I need and the series that I need. So the derivative of 1 over 1 minus x squared, I showed in the part that I just erased, is 1 minus x quantity squared. And I'm going to take the derivative of each term. So the derivative of 1 is 0. The derivative of x is 1. Derivative of x squared is 2x. Derivative of x to the third is 3x squared. 4x to the third, and so on. So this function and this series are identical. And look, I should have pointed this out before, but I didn't. It's not geometric. This is not a geometric series. Look, I don't have a constant multiplier. To get from 1 to 2x, I would have to multiply by 2x. And to get from 2x to 3x squared, I'd have to multiply by 3 halves x. So I do not have a constant multiplier. So this is not a geometric series. So it's kind of cool that I'm using a geometric series that I know to write a series that is not geometric. The others probably weren't either. I didn't even stop to pay attention. No, they weren't. They did not have a constant multiplier either. Okay, so let's write the general term now. I don't have any more room, so I'm going to write the general term up here. Oops. So it looks like each term is just going to have, we don't have any alternator, so each term is just going to have an n. 1, 2, 3, 4, 5. That just goes up by 1. And then I'm going to have an x to the n. Do those all work? Let's see. I'm going to start. I need to not have a power for x here, so I'm going to start with n being 0. Actually, you know what? Hold on. I'm not going to, I told you I don't like to do n first, so let's not. I don't have the other thing finished yet. Is this correct? Will an n down here and an n up here give me the right terms? And the answer is no. I need the power of n. Oh, I don't mean to draw a 0 there, but I need this power, these powers of n. I need the powers of x to be 1 less than the coefficients. It's a little easier to notice when I get into these bigger ones. 3x to the second. Oh yeah, my power of x is 1 less than the coefficient. 4x to the third. Right, my power of x is 1 less than the coefficient. So this power is actually that. Now let's see, can I start at 0 and be correct? Nope, that would not give me this first term of 1, so I'm not going to start there. If I start with 1, will I be good? Yeah. So starting with 1 will give me the n of coefficient of 1, and then it'll give me x to the 0 to start with. So there we go. There is our general term. You will have to be able to write the general term yourself based on the series that we have. You will not have to come up with this fully on your own. Okay, so that's the lesson, but we're going to have to do some practice problems. I'm going to stop this and get the practice problems ready, and then I'll do them with a video as well.